Today we want to talk about solving equations. And I want to talk about solving equations in my particular view of it. So no one here was in my algebra class, so you weren't raised in my tradition of solving equations. So that's why I'm just going to start from the beginning, the way that I think about solving equations. So we're going to start off doing problems that I know y'all already know how to do. So that's okay. And the way that I talk about it is not any different than what you've been talking about, but than what you've been taught before. So I'm not trying to do something new. I'm just trying to put a different spin on something old. So just trying to add to your thinking about solving equations. So from a certain point of view, you already do what I'm going to be asking you to do. That is perform inverse operations in reverse order. So what I mean, think of these inverse operations as the things that you do to both sides of the equation. So these inverse operations are the things you do to both sides. So this inverse operations business, this is where you do a thing to both sides. This is where you're going to be doing a thing to both sides of the equation to maintain balance. You might have used language where you cancel something from both sides. So a lot of times we think about canceling stuff out. I do not favor this language very much. I do not like talking about canceling something from both sides, but it's language that you might have grown up with. So I want to include that this is that. This inverse operations in reverse order is still these same kinds of traditions. And all this falls in the category of maintaining balance. So there's lots of things. This inverse operation is still maintaining balance, doing things to both sides, canceling something off of both sides, maintaining balance. I want to phrase it in this way, inverse operations in reverse order, because I want to be able to read the order of operations and I want to think of things in terms of function and inverse function. That's my reason for going with this inverse operations. I like to think about order of operations. And I like to think about function and inverse function. That is why I favor this kind of thinking. Operationally, not new. Thinking might be a little bit different, but it's the same core principle. Nothing fancy going on here. So let's think about operation, inverse operation, function, inverse function. If you have the equation x minus 3 equals 8, what do you do to both sides? We add 3, right? We see that x has had 3 subtracted from it. So something minus 3 is equal to 8. And so we're really just playing with the 2 out of 3 game. If x minus 3 is equal to 8, then x is 8 plus 3. So some of you might be thinking, we will add 3 to both sides. I don't know how you would write it. Y'all will write things differently. Some of you will write underneath like a plus 3 and a plus 3. And then you'll say x equals 11. Some of you will even go so far as to cancel out the minus 3 and the plus 3. This would be if you're on team vertical. You learn to just put the thing that you're doing underneath. Some of you came from a teacher that definitely read the book, because it's hard to line things up vertically. So some books would be like, oh, what you do is you take the x minus 3, and then you put plus 3 over here. And then this is equal to 8 plus 3. And then we have maintained the balance. And then you'd be like, oh, x minus 3 plus 3 is 0. So then you would write the same thing. You would still write x equals 11. You'll notice that I wrote my equal sign almost under the equal sign. This is the result of someone who had lost points because their equal signs didn't line up. It's a little bit off because that's me trying to rebel against the bad instruction that I had before, or the all too picky instruction that I had before. It doesn't really have to line up, does it? And my keyboard is like, oh, yes, it has to line up. It's like, oh, what if it doesn't line up? Then I take off points. I'm like, oh, fine, if you're just going to hit me. Yeah, so. Yeah, so some people are very into form that way. Some of you think about it even, maybe think about it even differently. Some of you think about move the minus 3 to the other side. So you look at x minus 3 is equal to 8. You want x by itself. So in your mind, you're thinking, move the negative 3 to the other side of the equation. And so you would write x equals 8 plus 3. And then you would write x equals 11. And if you're rebelling against your teacher, you put them a slightly off kilter. So this might be the tradition that you came from. You imagine taking the 3 on one side and moving it to the other side. I demonstrated this once in a class, and one of my students reflexively said, change the sign when you cross the line. It's like they couldn't help it because their teacher had programmed them so hard with this moving idea. It completely broke down. They couldn't divide their side. It's fine. It's fine. I can work with that. It's fine. The only thing that matters is that when you see x minus 3 equals 8, you know that the answer is 11. As far as what you write, if in my classroom, I don't know if I'll ask this on a test or something like that. If I ask, they give you the problem, x minus 3 equals 8, you just need to tell me that x equals 11. Even if I say, show your calculations. I didn't even write x equals 11. Because the instructions would have said solve for x. So if you say 11, that's just finishing the sentence. What is x? X is 11. You don't have to write the whole sentence. I want to know that you can come up with 11. If you need to write something down to get there, then write that down. If you can look at this equation and say x is 11 and just write the 11, then just write the 11. The point of the math class is to not have to write all the friggin' math all the time. Even when I say show your calculation. Because in this problem, Your calculations were the empty set. You just looked at this and observed that the answer was 11. Your calculations don't exist. You don't have to write them. What you don't want to do is subtract 3 from both sides, write 11, and then erase all that stuff. As if I can't see that. You know what I mean? It's like over on the side of the paper, there's at one point you have to do like 17 times 3, and you got to go over on the side of the paper and you write 17 times 3, and you're like, oh, 21, and then 3 times, so 51. And so it's 51, then you write 51 over here, and then you go and you try to erase this. Right? You try to erase it. Why are you trying to erase it? Are you trying to impress me that you knew 17 times 3, like you didn't have to write it down, and you're trying to fake it? That's ridiculous. And second of all, I can see that you wrote it there. It's one thing if you erased it and then wrote some other shit on top of it. It's like, oh, you needed the space. That's cool. I get that. I get that. It's when you erase it and it's like you're hiding the evidence. It's like, oh, we don't look over here. As if I'm going to see, oh, I see you had to write down 17 times 3 minus 10 points. If I see 17 times 3 off to the side like that, I'll be happy. I go, oh, you recognized that you needed to write something down, and so you wrote it down. It's like when I see you erase it, I can see the trauma of your teacher's like, oh, why did you write this? This doesn't make any sense. Blah, blah, blah. And they're going, ah. And so your PTSD is like, oh, I got to erase that. Crazy. Feel bad for you. It's probably not. But if you feel like you need to erase it, you're like, well, no, I can't leave it there. No, it brings back too many bad memories. I'm going to have to erase it. I'm also not going to make fun of you for that. You got to do what you need to do what you got to do. You needed that 51. However you get that 51 is okay with me. And you still come out to 11 at the end. I don't know why you need 17 times 3 to come up with 11 in this problem, but if that's the way your mind works, who am I? Who am I? So the important thing here to note is that we look at what happened to the x. We subtracted 3. So the inverse of that is adding 3. X turned into 8 by subtracting 3. We turn 8 back into x by adding 3. So x turned into 8 by this operation, subtracting 3. So to turn 8 back into x, the inverse of subtracting 3 is we add 3. The equation is telling us x turns into 8 by subtracting 3. So 8 turns back into x by adding 3. This is just another way of thinking about the equation. Now, there's not a lot going on in this equation. So let's add some more stuff to it. Another set of inverse operations are multiplication and division. If 3x equals 24, what must x equal? 8. This is all we need to write if I ask this question on a quiz or test or a final exam or a post-graduation quiz. So I find out where you're working, fill up the place and you do that. And if 3x equals 24, you gotta solve this grade. If not, I'm going to go back and change your grade. I'm just kidding. No. It would be excellent. I mean, I would just find out where you work and try to do it in creative ways. Like you're working at Starbucks, or something like that. Can I have a name for the order? 3x equals 24. I go, what? I said 3x equals 24. You have until I pull up to the drive-through window. And then you hand it back. Yes, that's how it would work. So I would go up to the counter because I don't go to the drive-through. And I'd be like, oh, 3x equals 24. And then when you call out, you just be like, oh, x equals 8. And I'll be like, oh, you pass. So what do we do? What's the operation that we do here? Divide. So some of you on the vertical team would be like, I'll divide by 3, and so x is equal to 8, which is totally cool. I'm okay with that. Some of you are going to think of moving the 3 to the other side. Some of you will be in the camp. You'll see 3x equals 8. Or sorry, 3x equals 24. And you'll think about moving the 3 to the other side. So you'll be like, you just write x equals 24 divided by 3. All perfectly valid ways. The most important thing is that you come up with 8. The read that I want to put on this is that we turn, it looks ridiculous when we only have the one step. X turns into 24 by multiplying by 3. The inverse of multiplying by 3 is dividing by 3. So to turn 24 back into x, we would do the inverse of multiply by 3. We would divide by 3. Inverse operation in reverse order. Reverse order doesn't mean anything here because there's only one. I do want to point out with multiplication and division that we could have a problem written in terms of division. So for example, let's suppose that x divided by 5 is equal to 3. What is x equal to? Just based on observation, what is x equal to? 15. So we need to know, we already know x is 15. But we want some thinking behind. So if we're going to do behind coming up with the 15. So we're saying what divided by 5 is 3. The answer is 15. We know that. We're done with the actual problem. But we want to think in terms of math. What do we do to both sides of the equation? Multiply by 5. So some of you will be taking the x over 5. And you will multiply by 5. Some of you will multiply by 5 over 1. That's okay too. Some of you will be thinking of move the x, the 5 to the other side. So you'll see x over 5 is equal to 3. And you'll say, I'm going to move the x to the other side of the equation. And so you're going to write 3. It's divided on this side, so it'll be multiplied on this side. Some of you might look at this and say, well, the x is being multiplied by 1/5, so I'm going to divide by 1/5. So some of you are looking at this completely differently. You see a 1/5 times the x is equal to 3. And so you're going to divide both sides by 1/5. We know that 3 divided by 1/5, when we're dividing a fraction, we multiply by the reciprocal. So write this as 3 times, almost out of space. Dividing by 1/5 is the same as multiplying by 5/1. Was anybody thinking about dividing by 1/5? Incorrect. Everyone who said multiply by 5 also said divide by 1/5. They are the same thing. Don't be fooled by the 2-button calculator thing. In thinking in terms of inverse operations in reverse order, we could say that x got turned into a 3. The only operation we performed was dividing by 5. So to turn the 3 back into x and find out what it is, we would perform the inverse operation in reverse order, which is to multiply by 5. How's everybody okay? Of course, all we've done is like add 3 and then like divide by 5. We're all good. Everybody's like, oh, yeah, we're fine. Let's go to our next set of operation inverse operations. So exponents and then radicals. This is the point where we are unnecessarily complicating things. Radicals are just fraction exponents. Radicals are just fraction exponents. So if we have an equation that says, say, x cubed is equal to 64, what do we do to both sides? Do what? Well, it's already cubed. The inverse of a cube is a cube root. Well, but actually, before we even do that, what's the answer? What to the 3rd power is 64? 4. That's the important part. From a just solving the equation standpoint, that's the important part. We can get to 4. But we need to have some operation that goes around with this. So we want to think about doing the inverse of a cube. And so that's a cube root. So we could write it this way. The cube root of x to the 3rd is equal to the cube root of 64. And then from here, the cube root of x to the 3rd, those are the inverse operations giving you an x to the 1st power. That's what the inverse does. Get you back to where you started from. Cube roots of a cube is just the x. The cube root of 64 is 4. This one we probably just recognize that 4 cubed is 64. We just recognize that 4 cubed is 64, but we want to know the operations in case I ask some kind of messed up question. In case I'm like, oh, x cubed is equal to 67. And we know that 67 is not a nice cube. And so we'll be like, oh, 4 point something. And then I'll be like, oh, can you be more specific? And you'll be like, oh, all right. And then, all right. Let's find the cube root of 64. Oh, 67. 4.061. Then I'll be like, I'll round it to the nearest unit. They go, son of a, that's what I said with the 4. I'm just kidding. I'll be like, I'll round to the nearest 100, let's say, 4.06. So we will want to recognize the inverse operation so that we could do a cube root of both sides. I'm going to do it my inappropriate old school way. Math teacher always complained about my equal signs not lining up, but would still pull this shit on us. I go, come on, man. You can't put a whole equation under the cube root. Then they're like, oh, just did. Son of a. So what we want to do now is I want to think of radicals not as these weird radicals, this weird radical notation. I want to think about radicals as fraction exponents. Radicals are fraction exponents. The index is the denominator. The index of the radical is the denominator of the exponents. The index of the radical is the denominator of the exponent. A square root of x is a 1/2 power. When you write fraction exponents, if you're going to write it as a superscript, I recommend side-to-side fractions when you're writing by hand. So write your fraction exponents side to side. When you're typing, so when you're typing and you make an exponent and then make a fraction in that exponent, it usually comes up vertical. But when you're typing, it's much easier to see the exponents, top and bottom. It's harder to switch fonts when you're writing by hand. Or in single line syntax, we could say x to the 1/2. So it's hard to text exponents around. So we need to know our single line syntax. So during the test, if we need to text someone what the answer is, we know how to note exponents. When we have a square root, the index is 2. It's an implied 2. Every other kind of root, like a cube root of x is a 1/3 power. Or we can write in single line syntax x to the 1/3. Note that when we're doing single line syntax, I'm not making a superscript. That's what that little arrow pointing up is. That's what the caret is. The caret indicates a superscript, or it indicates an exponent. So instead of writing the superscript, we just put the caret. Sometimes students will put a caret and then a superscript after it. It's like, oh, that's a little too far. That's too many superscripts. That's like a superscript. They don't cancel out, but it just goes too far. Superman is plenty. We don't need Superman. So if there's no index, it's a 2. Otherwise, we'll just see what the index is. So what this means is that if we want to figure out the cube root of 64, we could have also written this as 64 to the 1/3 power. Over here, this 67 to the cube root of 67, we could have written as 67 to the 1/3 power. There's 67 to the 1/3 power. I got the same thing. What if I don't have the parentheses? What happened here? Yeah, so if I don't put the parentheses, I didn't tell the calculator, I want the 1 to be divided by 3 and then make it the exponent. The calculator is just following the order of operations if there's no parentheses. It says 67 to the 1st power, finds the result of that, and then divides the result by 3. This is just 67 divided by 3. So without the parentheses, now I realize order of operations is also not something that I've talked about in my algebra class with y'all because y'all weren't in my algebra class because I don't have one anymore. No one at Skyline has one anymore. But man, had you been there, we would have not read parentheses as an operation unto itself, but as a way to change the order of operations. Normally, exponents go before division, but in this problem, in this expression, I want 1/3 to be the exponent. I want 1 to be divided by 3 first, then make that the exponent on the 67. So normally, exponents go before division. So if I have 67 to the 1/3 with no parentheses, the calculator is going to read exponents first. And then it's going to divide by 3. Your calculator is just doing what you asked it to do. You asked it to raise 67 to the 1st power and divide the result by 3. If you want to change that order around, you need to put the 1/3 in parentheses. The cube root of 67? Yeah. So on the calculator, if you want a cube root, that's going to be in the math menu. So press the math button. Oh, first type in your, no, it goes first. Press the math button and then scroll down. Number 4 is a cube root. You can't put the 3 in front. We don't want to put the 3 in front. If we just type 3 and then the radical, this is 3 times the square root. So that's not what we want. If you want to use some other index, like if we had to calculate the 5th root of 67, you type in the index and then use your generic index. See the 5th entry. So it's 5, and then if you see a 5x root of, then the number in front of the radical is the index of the radical. So the fifth root of 32, oops, I put parentheses and I didn't need to. The fifth root of 32 is 2. So that's what it looks like to do a fifth root. You get a cube root button, but everything else after that is just. So 32 to the 1/5 power is 2. A fifth root is a 1/5 power. And this is all because 2 to the 5th is 32. So notice that the inverse of exponents is fraction exponents, which is just another exponent. This is why it makes sense. I'm going to phrase it in a way that you may have heard. This is a very common phrasing that I hear. When you have an exponential expression raised to another exponent, you multiply the exponents. Sometimes we say this in math when we say x to the n to the m is x to the n times m. When you have an exponential expression raised to an exponent, you multiply the exponents. N and m sound too similar, so sometimes I think x squared cubed is x to the 6th. You multiply the exponent. You have an exponential expression raised to an exponent, you multiply the exponent. So if I have the cube root of x cubed, we know that this is equal to x. The way we can think about it is we could think of x cubed being raised to the 1/3 power. 3 times a third is 1. We multiply the exponents. Because multiplication is commutative, if I've got the cube root of x and then I cube it, that's x to the 1/3 to the third. We multiply the exponents and we get x to the 1. So if we want to solve an equation and there are radicals involved, we can think of them as fraction exponents. So for example, if I have an equation, the 7th root of x is 1.098. That 7th root of x is x to the 1/7 power. That's the way we could think about it. The reciprocal of 1/7, the reciprocal exponent, is a 7th power. So we're reading this as x to the 1/7 power. So our maneuver is to raise to the 7th power. One seventh times 7 is just an x. And I'll take the 1.098 and raise that to the 7th power. 1.924. If I want to check my answer, I can just find the 7th root of 1.92405. 112. No parentheses. Back to 1.098. Or I can take my 1.924 9240500. Oh, I keep saying oh. 0. Thank you. 12. If I raise that to the 1/7 power, 1.098. So it all works out. That's the great thing about solving equations. You can always know if you're right or wrong by taking what you think the answer is, seeing if it fits in the equation. In terms of inverse operations in reverse order, what I would write for this equation, I would say x got turned into a 1.098. The only operation we did was a 1/7 power. You could also write a 7th root of, as long as you remember that the inverse of a 7th root is a 7th power, or the inverse of a 1/7 power is a 7th power. So to take a 1.098 and turn it back into an x, the only operation we need to do is raise to the 7th power. The inverse of an exponent is just some other exponent. I prefer to think in terms of rational exponents. I prefer to think of fraction exponents. If you have a way of solving powers that involves using radicals, that is what you should do. Inverse of an exponent is a reciprocal exponent. So in these equations up here, when we had x cubed equals 67, the operation was we raised to the 3rd power. So the inverse of this, to turn 67 back into an x, is a 1/3 power. Just inverse of an exponent is the reciprocal exponent. Inverse of an exponent is the reciprocal exponent. This way I don't have to mess with these radicals. This takes us through our core arithmetic operations: addition, multiplication, exponents. Those are our 3 core arithmetic operations. I know I didn't say subtraction. I didn't say subtraction because subtraction is just the inverse of addition. Subtraction is just addition of opposites. I didn't say division because division is just the inverse of multiplication. Division is multiplication by reciprocals. I didn't say radicals because radicals are just fraction exponents. The inverse of an exponent is the reciprocal exponent. This takes us through all our core operations. Sitting at the base of all of our operations is addition. Everything is based on addition. Multiplication is the shortcut to addition when everything is the same. Multiplication is repeated addition. Exponents is the next level up. Exponents is our shortcut to multiplication. Exponents represent repeated multiplication. So here are our 3 core arithmetic operations and their inverse. What we need to do now is look at equations and expressions where these operations are combined. So we need to know the order of operations. All right, let's take a break, come back and we'll talk about more than one operation and why even exponents are kind of annoying.